All right. We are now talking about gauge fields. Gauge fields are going to be the things that describe photons, right? So we went from scalar fields, we quantized those, complex scalar fields. We then went into spinor fields. We derived the Pauli exclusion principle. Now we're at gauge fields, and what we're going to see in gauge fields is something really, really fun and interesting. And this is something. It's also something that's not mentioned in the book. By the way, for those of you who are new, this is the book we're following, No Nonsense Quantum Field Theory. Now let's get right into the material. But before we do that, hit that like and subscribe button. Let's get to it. All right, gauge fields. Gauge fields are going to describe photons. Okay, I'm just going to come out straight out. Gauge fields are we can think of these as vector fields. So let's actually think of these as vector fields, right? So what I'm going to actually rename this to vector fields. Simply put, a vector field is something that is a vector at every point in space and time, right? Now, how do we construct a vector at every point in space and time? That's a pretty simple question to ask. It's also pretty non-intuitive when you start to dive deep into the weeds here, because what you need to be able to do is you need to be able to construct a coordinate system at each point in space so that you can describe each vector, okay? Because vectors have components. It can be a multi-dimensional vector. It can be three-dimensional vector. You have vector fields. Vector fields are very useful in helping us describe the real world. So we talked about scalars, we talked about spinors, now we're talking about vectors, okay? So in order to construct these little coordinate systems everywhere so that we can describe each vector in the vector field, we need to be able to pick out basis vectors, right? So we need basis vectors to be able to construct our vectors. So we need basis vectors at each point in space. And so the way we do that is we say, okay, at each point in space you have x, y, z dimensions, okay? And then you have, at x, y, and z, you have three basis vectors. And we do this by saying, oops, here's my pointer. These are what our basis vectors are going to look like, okay? For every upper index, we have, so every upper index is going to have its own associated vector with it, okay? And so we can go, so we say we have, okay, this upper index 1, all the vectors associated with that upper index are going to look like this. You can see they're all the same. Mu here is going over all space-time, right? And so same thing here, 2, for E2, we can have vectors that look like this. And so this is going to be useful to us. And here's why. What we want to be able to do is we want to be able to say that, so essentially what we're doing is we're labeling the axis, we're labeling the axis with the upper indices, and we are identifying the point in space at which the axis is, at which the coordinate system is located. Okay, and that's with the lower indices. And typically, what you see is the upper indices as being Latin index, and the lower indices as being Greek indices. Right, so mu is Greek, and then these tend to be like A, B, C, and D, and so forth. I and J is something you'll see a lot also. So if we pick, say, this guy right here, that's going to be this vector, okay? So that's going to be, say, our first basis vector. Our next basis vector is going to be pointing in an orthogonal direction. So it can't be this guy, right? It has to be, let me back up. So if we pick this guy here, say 1, so say we pick this guy here. Actually, yeah. So say we're picking this guy here. So if we want to construct a basis vector, we want to construct a basis. If we want to construct a basis system, we want to be able to find the next vector that is orthogonal to this guy, right? So we could pick this guy right here, for example. Okay, because these two vectors are orthogonal to one another. Right? If we picked these two guys, they're also orthogonal to one another. Right? The idea, though, is that so if we take this guy here and this guy here, and we perform an inner product on them, when we perform that inner product, if you notice here, we get 0. Okay, that's the orthogonality condition. Right? If we're summing across this guy, these two guys, so this guy here and this guy here, right, we get 1. We don't want that to be the case, right? Because we're looking for orthogonality. So when we pick one of these, right, we have to pick one in which the next basis vector in which we get orthogonality, because that's what we want to use to create any vector within that space. Okay. Hopefully that makes sense, right? If it doesn't, let's go through that. Let's go through that one more time, because I really, really want to bring this home. I really want to. If I repeat myself, that's okay with me. Anyways, we can think of this as, say, we have E1 x. Okay. This here has to be E2, right? But it has to be E2. It can't be X, right? It can't be X. It has to be some other one, say T, because if it's X, then we've identified two basis vectors that have a condition where we take the inner product and we get 1. We want to be able to take the inner product and get 2, so that we can have them orthogonal to one another. Okay. So, and these guys are what are called structure constants. They are sort of defining the structure of the space in which we're going to be able to describe vectors in this space. Okay. Before we move on, we want to talk about just a brief review of what we have gone over when talking about these gauge fields or these vector fields. So the idea here, again, is that we had solutions, and the solutions were proportional to an exponential, and through this exponential relationship, we were able to get this dispersion relationship. Same thing here, we got this from our Lagrangian, this condition, and when we imposed masslessness, this is a masslessness condition. Again, this was something that we went over before. We were able to get this Lorentz condition. Right? The Lorentz condition tells us that the derivative with respect to our solution is going to 0. Right? This is so we sum over rho here. Okay. Okay, and so then what we do is here, so once we get here and we impose that, and we say that if we're trying to describe some particle that's moving in the z direction, say, the 4 momentum vector component, the first component looks like this. This is what the temporal component looks like for that particle moving in z. And then from there, this is what our momentum 4 vector looked like. Okay, from the Lorentz condition, or so from this Lorentz condition, we were able to get this here. This is a relationship between the form momentum, so that's this guy here, relationship between the form momentum and these structure constants. Okay, structure constants contained internal structure and space-time structure, right? We talked about this being the upper index of the space-time constants, and this thing being the lower index of the space-time constants or structure constants. And from there, if we then specified what the z direction was, we were able to get vectors that look like this. So this is sort of our structure constant 4 vector. Okay. And notice here that if we're traveling in z, these are essentially opposite of one another. Okay. That the structure constant 4 vector is basically flipped. Right? It's a flipped version of the momentum 4 vector. Okay. And we've went all through a lot of that already. Okay. So now, moving onto this side here. So again, the upper index of the structure constants are going to refer to internal structure. This is just vocabulary, right? And the lower index is gonna refer to the space-time structure. Anyways, moving on, if we sum over the space-time structure, what we're gonna get is this right here. And I have these over m, right? Let's erase these over m's actually really quick. Because when we do this multiplication, this multiplication, we get something that looks like this. We get m squared, right? So we can normalize these. By putting everything over m, so that we get this guy right here. Right? We're not really summing over space-time here. We want our covariant form or our upper index form to have this relationship with where this is 0 now. 0 if normalized. Right, so that's what the normalization means. And so what we get, so to make the structure 4 vector, to make it, we get this. Right, so, and notice if we're massless, then there really is no 4 vector. If we're massless. Because you can't divide things by 0. That's something interesting to note, and something we'll get into later. Anyways, to put things a little bit more in a pictorial sense, right? So what we've done is we've said at every point in space, we've established a little coordinate system. And the little coordinate system has an E1 component and an E2 component, right? And it also has an E3 component. Now we picked our particle, which is being described by a vector in this case. These are vectors. We picked our particle to move in a particular direction, right? And that direction is the z direction. And that z direction is say this direction right here. It could have been this direction, could have been this direction, right? I'm just picking it to be this direction. And what we're saying is that these two vectors, they're orthogonal to one another. Perfect, right? You multiply this by this guy, you get 0. Great. This guy here was our other vector that we found to be true, right? Or other vector that we calculated to be our other basis vector, right? So the motion of the particle contributes, or the direction of the motion of the particle contributes to constructing our coordinate system. And that's what these vector fields look like, right? So you have vectors, essentially, making up our basis system, as opposed to spinors. If you remember spinors, these guys, we had things that look like these, right? But we also had this additional e to the minus imt, also describing our spinor solutions. Okay, this was for spinors. And that's what made those guys different from these fields. So now what I want to do really quick is we want to take this guy, and this guy. We want to sum over the labeled indices, right? Not the space-time indices. And we want to find an interesting relationship here. So if we sum over the A, and sometimes, some cases, this will be an R. I'll put an R here. Let's do that in black. I'll do R, because we're gonna see this. We're gonna use R later. We're summing over R. So essentially, what we're doing is we're taking this guy, and this guy, which are right here, and we get this. This is going to be an interesting relationship because we're going to find something later on called the completeness relationship. It's going to make these guys equal to something else. It's going to look an awful lot like something that shows up in GR. Okay, and I've noted this before. It's not directly related to GR. There's a whole field of study, a whole field of research going into trying to understand GR within the context of quantum field theory, and quantum field theory within the context of GR, trying to reconcile the two. Because the narrative right now is that it's very hard to reconcile the two. One describes fuzzy space-time, where the other one is reliant on smooth space-time manifold. So it's very hard to it's very hard to reconcile these two theories. But nevertheless, we find mathematical analogs, mathematical hints that look very similar in one area of physics and another area of physics. And the completeness relationship is what the completeness relationship is going to help us do is understand that we're going to have a tetrad system. Tetrad system is something that's seen in GR, where you create these little coordinate diagrams at every point in space. That's what these tetrads are going to do. These guys essentially are the tetrads. Right? I'm speaking sort of analogously, if you will. They're not exactly tetrads, right? In the context of quantum field theory, they're not tetrads. In the context of GR, we can call these things tetrads. But again, what I really want to do here is sort of hint at what the mathematical analogs are and how they look very, very spookily similar to one another. Okay, so we're going to have these things called tetrads. We're going to have this thing called the completeness relationship. The completeness relationship is going to take these things that look like tetrads and equivocate them with something that looks like a disturbance in a gravitational field, right? And I'll go more into that in our next video. But anyways, I'm pushing on 20 minutes here. If you like this kind of content, please hit that subscribe button and like this video, and I'll see you guys in the next one. Bye.